Julian for the invitation. And okay, recording in progress. So I will share my screen. I think that you need to allow that, Julian. Actually, I'm gonna share just one specific.
Of course, should be
oh yes, now I can. Okay, so I'm just gonna copy this and put on the chat. Here's the chat. Let me put it here. So this is the path to the notebook, and also the GitHub is here. You guys can go ahead and see. And welcome everybody. This is a Turing workshop, and also a workshop for using Turing as a tool of Bayesian inference. This whole content is Creative Commons license, so you can use it whatever you want it. Just take a look at the license, but it's a very permissive license. And like everybody that I do, everything that I do it as a Creative Commons content. A little bit about myself. I'm a PhD. This is my website with some projects and a CV. I'm associate professor at Universidade 9 de Julho, Uninove, located here in São Paulo, Brazil. I teach undergraduates machine learning. I still use Python, but I'm trying to migrate the whole content to Julia. These are all links that you guys can go ahead and click. The content is all open source and Creative Commons, so you guys can use it, modify. And I also teach graduate students Bayesian statistics. I mainly use STAN, and scientific computing using Julia. This is a new course that I will teach starting in August. So I'm pretty excited. I will be mainly using Pluto Notebooks, just like the guys at the MIT Computational Thinking course do. So it's but the whole content in Portuguese. The reason I got invited for this workshop is because I made some Turing tutorials. You can find them online at this link. And also, you guys, if you want to connect it, I have a Twitter, but I just created to use the Twitter API because I wanted to gather some tweets for a project. And I rarely use it, but I use most LinkedIn, and this is my LinkedIn link. You guys can connect it. And just a little quick recap, what is Bayesian statistics? It's just an approach. I mean, a very good approach, a very good sounding approach, intuitive approach towards statistical inference, that you use the base theorems, that this theorem here, and where you have some prior distribution over a parameter theta, and you use it, you combine it with the likelihood of your data given your parameters, and then you have to divide everything by the normalizing constant that's also called evidence in some literature, for this to become a valid probability distribution that sums up or integrates to one. And this is what we call the posterior distribution. And it encompasses all the probability density of our parameters theta given our data y. This is Bayesian Statistics 101, very quick intro. And also you can use the posterior to understand your whole parameter density and to understand your whole data generative process that you are interested in, or you can use it to make predictions about future events. And the people in machine learning, they are not interested in inference, they just want the prediction. But with Bayesian statistics, you can do both. It's more computationally heavy, expensive, because you are now estimating a whole density, not just a small maximum likelihood estimate of the parameters. So you can use it as a machine learning framework, but hope you have some bang in your computer to handle it. And most important, there are no p-values. Most of the people don't know what p-value are, and most of PhDs don't understand what p-values are anyway. So they are not the probability of your null hypothesis given your data. That's all I'm gonna say about p-values. They are not what you think they are. So they are quite the opposite. It's the probability of your data given the null hypothesis. And also I have 4 books that are really wonderful. They cover the whole Bayesian world. I remember the first time that I opened it, the Bayesian data analysis. It was like going through Alice's rabbit hole. It was quite a journey, and I still have it. I use it all the time. It's a very good book. This one. These are also links you can click, and it will take to the editor or the Routledge, the book website. These are not affiliate links. I won't make any money if you click on those links. Go ahead. We also have the Statistical Rethinking. It's an amazing book. I really like the Richard McErith way of writing. He has a kind of English dark humor. I think it's quite nice. It appeals me. I only don't like the summary. It's quite complicated because he uses he gives like a permissive poetry license to not say like chapter 1 is about this. He gives like monsters and mixtures when he talks about mixture models and generalized linear models. And also we have the Regression and Other Stories by Andrew Gelman. This is the 2020 book. It's quite new and it's really interesting for beginners. And if you are interested on the whole sociological history about Bayesian statistics and Bayesian inference, this is a very good book. The Theory That Would Not Die: How Bayesian Statistics Cracked the Enigma Code, Hunted Down Some Submarines, and also survived half a century of bashing from Neiman, Pearson, and Fisher. This is a very interesting history. So these are the 4 books that I recommend. Now, what is Turing? So we also have some reference here. I think that you guys can see my mouse, right? Okay. We have some reference here at the bottom from everything that I cite here. Turing is an ecosystem of Julia packages because it has more than one package, and for doing Bayesian inference. And it's specifically, it's a probabilistic programming language embedded inside Julia. And you specify models quite easily. It resembles mathematical notation for when you read probability models. And also, like everything in Julia, Turing is fast. Tarek, who is one of the developers, also Shu, who is one of the founders of Turing, and the other guys, they did a whole benchmark with Stan, because Stan is the state of the art in Bayesian inference and MCMC models, Markov chain Monte Carlo models. And Turing is not as fast, but it's getting pretty close. So that's why I made the tutorials, and that's why I got interested in Turing, and because I was already interested in Julia as a scientific computing language. This is the whole ecosystem. They have a GitHub organization called Turing Lang. They have a lot of packages, but I will only focus on 5 packages. We have Turing.jl. This is the main package, the whole interface. That's mainly the one that you will use for everything in Turing. You just do using Turing. That deals with the most of the stuff that you need. We have MCMCChains.jl. It's an interface for summarizing, describing, inspecting, plotting, manipulating MCMC simulations. They have a very nice type called chains object that you can do all kinds of things, and it's a very nice interface. We have dynamic PPL, dynamic probabilistic programming language, which kind of specify the whole domain specific language for Turing. who Turing also is a probabilistic programming language. We have advanced HMC. This is where all the state-of-the-art Markov chain Monte Carlo algorithms they reside in Turing. So this is where you find your SMC, nuts, HMC, HMC dual averaging. Everything is inside this package. I will dive more deeply in those algorithms in a while. We have also distribution AD. The AD is for automatic differentiation, and it's the package that makes possible for Turing to evaluate any joint probability or probability distribution with respect to its parameters and get the log PDF, and most important, the gradient of the log PDF. And it can use either forward mode or reverse mode autodiff. I will also talk about this in 5.1. And these are the main packages. So how do we specify a model in Turing? We just use the model macro. And inside that macro, we specify variables that we want for Turing to sample. And we use the tilde. That's mostly what we use anyways in mathematical notation. And if we want to have a variable take a specific deterministic value, not a probabilistic value, we use the equal sign, and which means that the variable does not follow on a specific probability distribution, and it's a deterministic value. And for example, and Turing will perform inference in all the variables that you specify using the tilde notation. For example, suppose we have a coin, and it's an unfair coin, but we don't know. And then we say, okay, the probability of the coin being fair, it's a beta 1,1. That's a very weakly informative prior. Actually, it's a flat prior. It gives equal weights to all the probabilities between 0 and 1. This is the function of the beta distribution. And then we say that the coin flips are distributed as a Bernoulli trial with probability P. So this P parameter has a prior, and the coin flip is the data. And then I just generated some random coin flips using a Bernoulli with 0.7 of probability, so it's an unfair coin. And I generated 100 draws. So this is my data, and then I specify my model. I say model. I give the model a name. I specify its parameters. So it's just the coin flips or epsilon, or sorry, epsilon or y as a data. And then I say that equals a begin and an end. So begin, and then I specify everything that goes inside of the model. So for example, I have the P distributed as a beta. So I kind of do like a copy paste from the mathematical notation. And then I do a for loop for every observation in the whole length of our observations. Coin flip is distributed as a Bernoulli P. And when I do that, I can then sample for it. I will explain how to specify a sampler and what's this 100 mean. And then I can have summary stats on that Markov chain sample. And this is the parameter P. It has mean 0.7, pretty close to our ground truth that was 0.7. And this is the standard deviation. And then we have effective sample size, R hat, and everything that I won't cover today, but it's on the books and the reference that I cited in this notebook. So this is quite nice because it reads like math notation, because this is what you find in science papers or in math papers or in modeling papers. You find that how the authors or the researchers specify the model. And when you go to define the model in Turing, it's easy. It's like one almost one-to-one interface between the probabilistic math modeling notation and the computational notation. So this is quite nice. Okay, then once we know how to specify our model, how do we sample for it? In Turing, the nice thing is that we can have several samplers, and here is a link for you guys to see all the samplers. There is also important sampling that I did not cover here that you can do it. And this is something nice because Stan has only HMC. It's really fast. It's really robust, but it only gives you one sampler. It's HMC. It's kind of like the Ford black model. You can have any color you want, being black. You can have any sampler you want, being just HMC. So I created some radar buttons here that you guys can click. And the most naive one, it's Random Walk Metropolis Hastings. This is the MH. And then if I click, this is kind of a very nasty if. You can do better things with the match.jl, but yes, Matthias, can you vectorize the for loop in the model? Yes, it's on here 5. I will cover this. Better tricks to avoid for loop inside model. I will cover this briefly. Yes, but you are totally right. We can vectorize and we can have huge gains with vectorization. So we have particle Gibbs. This is a PG, and it takes an argument that's the number of particles. I just put 1 because I can do this, and you can see the computation real fast. And we have sequential Monte Carlo. I forgot to describe it here, but we have SMC, sequential Monte Carlo, that does not take any parameters. You can specify if you want to, but it's not mandatory. You don't need to specify. HMC, you have to specify the epsilon and the L. And in the HMC literature, you'll find it the leapfrog step size as an epsilon. It's the size of the steps in the leapfrog symplectic integrator that HMC uses. And also you have the number of leapfrog steps. That's how much steps will your integrator will accomplish to calculate the Hamiltonian trajectories inside the whole probability space. So this is HMC. It also runs fast, and it will calculate the mean around 75. And then we have the HMC dual average from Nesterov algorithm that it calibrates automatically the epsilon and the L, the number of leapfrog steps. You don't need to do that. So you just supply the number of samples used for adaptation that I call NA, your target acceptance ratio, that's somehow related to Metropolis acceptance rate. We usually use 0.65 because it was proven that it is the best asymptotically acceptance rate that Hamiltonian Monte Carlo can give you. And you can also have a target leapfrog length that is generally called lambda. And then you can click this and it will also 10, 0.65, and I put it a lambda of 0.3. Oh, sorry, 10, yes, 0.3. So this is kind of the standard parameters. And then we can have the nuts. That's the new no U-turn sampling. This is the algorithm that Stan uses, and this is the state-of-the-art Hamiltonian Monte Carlo algorithm for exploring a whole posterior density geometry. It's pretty efficient, and it's very good. This is if you don't know which one to specify, just go nuts and you won't fail. This is very good. And you specify also an NA, the number of samples to use as adaptation, and a target acceptance ratio, that's the delta. I generally specify half of my samples as the number of samples to use for adaptation, for warm-up. And I also specify the target acceptance ratio as 0.65. These are also the defaults in Stan. So I pretty much don't go overboard from the Stan defaults using Turing. And you click here and then it already put like the nuts for me, and it estimated also around 0.7. And so the model, how you sample, you just use a method, you pass in a Turing model with the underlying parameters. This is coin flips, that's our model takes. Our model was named coin, and it takes an array that I named coin flips. And then I specify my sampler here, that's one of these guys here. And then I specify how many samples I wanted for the MCMC to generate it. So here it's just 100, but you wouldn't do that in the real world. You would put like 4,000, 2,000, way more. I'm just putting like small numbers for the notebook to run fast, for me to have this kind of experience with you guys. But in the real world, please use a lot of chains, a lot of samples, and also a lot of chains. I will cover running more chains now. So more chains, I want more chains. You can have more chains. You can run chains in parallel, either using multi-threading stuff with the threads.jl. That's the Julia standard library package for multi-threading. And also remember to read the multi-threading Julia documentation, because you need to either set an environment variable as Julia, I think it was num cores or something like that. Somebody please correct me in the chat. And you also, you launch a Julia console using Julia number of cores or number of threads equals something. And also you can use distributed.jl. This is the other package. Yeah, thanks guys. Julia num threads. That's the name of the game. Yes. And the distributed.jl, it uses the MPI interface. That's the message passing interface. And you run multi-process, not multi-threading, it's multi-process. And if you guys are running a model in a cluster, I think that you would prefer to use the distributed.jl standard library package in Julia than the threads.jl. And if you are using MCMCDistributed, don't forget to do the macro everywhere, and also the add proc stuff that you can find in the documentation for distributed.jl in Julia. And what you do, it's just another method of sample. I have sample a model, that's a Turing model with the whole parameters. Can you guys hear me? Is anybody have trouble with the sound? If you are having trouble with sound, click join with computer audio. Maybe that will solve it. So it's just another method signature for sample. You specify your model, a sampler, that's the Metropolis Hastings, nuts, or something. And then you specify an MCMCThreads or MCMCDistributed, the number of samples and how many chains you wanted for your model to run in parallel. So for your model to run, and it will use all your parallelizable cores that you have available. And this is how we do it. We say, okay, now I'm creating a new MCMC chain object, it's the chain coin parallel, and I say, okay, sample for my coin model using the coin flips arrays as an input using a Metropolis Hastings sampler. And now you are gonna run this multi-thread, 100 samples, choose two chains in parallel using multi-threading. And then when we run this, it is very fast. It already made inference for our parameters P, the probability of the coin. And it's around the ground truth, 0.7. And also we can have like 1,000 samples, for example, or we can even do like 10,000 samples. It's really fast. And we can see now that Metropolis Hastings is not so good. It still doesn't have it is still not converged to the ground truth, that's 0.74. And we can use another sampler like MCMC, like NUTS or HMC. If there is any questions, please feel free to interrupt me or ask in the chat. I have the chat right on the side of the screen that I'm kind of monitoring. I think that for now, it's the basic stuff, it's okay. Most people already have run some of models, Turing models using this kind of signature. And now let's talk about some stuff that it's not very clear in the Turing documentation that it took a while for me to find out. So how do we run a model with no data? How do we do the prior predictive check? And it's very, very important for us to analyze if our priors make sense. So we do something called prior predictive check. And this is based on the Gelman et al. 2020 Bayesian workflow paper. And I'm kind of making like, I'm simplifying it a lot. The whole diagram in the paper is more complex than the whole, than this. It's huge. It's like, has a lot of steps. It's like the full Krebs circle. It's way more complex, but for our purpose, just imagine that we have 3 states. We have the model specification. We have our model. Then we materialize our priors. We say, okay, our priors is this and that. And then we run Markov chain Monte Carlo and we make a posterior inference. It's not linear, the whole Bayesian inference model process. So you go kind of back and forth. When you go from model specification to the prior, you go back and forth, you do the prior predictive check. And when you go from that to the inference, you make the posterior predictive check. So these are what we call the predictive checks from your model and how it resembles the data generative process. And there's a lot of stuff for you to read here in the notebook. Please feel free to visit afterwards and do a whole reading. This is quite easy in Turing, but it's not so easy to find in the documentation. We need to create a prior distribution for a model. We just replace what we use as a MCMC sampler as the NUTS or Metropolis Hastings, and we supply a sampler called prior inside the Turing. So this is our chain with not using the likelihood, just using the prior distribution of the parameters. And I generated 100 samples. You can also use the whole multi-threading signatures here if you want to, or the distribute, it will work. And once we have that, I just specify, I run a predict function in my, using a chain and also using my model. So I have to instantiate a vector of missing data. Then I use missing, and I just have one observation. You can have more if you want more robust prior predictive checks. And then I call predict. I call the model in the missing data. This is the prior prediction. And then I do the check. I run predict. I pass our model that has the missing data, and then I pass a chain that I run previously using the prior sample. And then this is a chain of objects, and I can do summary stats on it, and I can see that my priors, they are okay. They have a standard deviation of half, and the mean around half. So it kind of resembles or captures the whole possibilities of the parameter P from my coin. So we will do this, and this is kind of scalable. If you have more complex model, you just have to specify more missing data, and then you run the model using a prior as an sampler, and then you do the predict in missing data, and then you instantiate a model with missing data, and then you do a predict using the missing data and your prior chain, and that will give you a prior predictive check. You can do the same with the posterior. You just specify here a real sampler, and you can do the same and with posterior predictive checks. You can find those here in those tutorials. I explain how to do posterior predictive checks also, but if you understand how you do it the prior, it's quite easy. It's the same method for doing the posterior predictive checks. You just use like real samplers instead of the prior. You use the likelihood for your Turing model. Oh, that's so. Force Brew is saying, okay, how do we interpret our results from the prior check? Why is the results from the summary show that the priors are fine? I mean, generally we would plot them. So, for example, we have the prior check. I can plot it, and you will see that. Oh, I have to generate more. Let me generate like 100. Oh, and that's when you have some problems when you try to do stuff live. So, okay, that didn't go very well, but the purpose of the prior predictive check is to see if our priors make sense, if our data just from the prior distribution is not generating something strange like a negative age or a distance that's thousands of kilometers instead of meters. So this is the whole point of doing a prior predictive check, is to see that if your priors make sense. Matthias, can you just sample more draws from the prior P? Yes, we can do that. Where is the prior? Oh, it's up here. Yes, we can do that. We can put like 1,000, and it will generate more priors. But the thing is that we need to expand the missing data. dimensionality, and somehow I kind of forgot how to do that, or I'm doing something strange and I'm getting an error. But go to the tutorials and go to the Turing documentation that you will find how to do more robust or more large prior predictive checks. Yeah, that's the whole deal. I get just one draw from every pre-drawn from the prior. Yeah, that's what I'm doing here. Now let's see. Okay, I have this whole chains objects that are my sampling results from a Turing model using either the prior or using a MCMC sampler. And now what I can do with this? I can do several things. First, I can spec the chains with summary statistics or using quantiles, like the median or the 95% quantile and everything. So if I have my chains object and I just do like a summary stats, I will get something similar to the data frame summary stats method. If you guys are familiar with data frames in Julia, it will give me the mean, the standard deviation, and also will give some Markov chain metrics. Yeah, Thor, thanks. So something that's interesting about this tutorial is because I have in the audience people that are way more experienced than me in Turing. So I thought that I would learn a lot in this tutorial also. So what Thor is doing is that, yeah, because I have a lot of things, of figures, I probably will need to do like a plot, vectorize, or do something to account for all those figures that I'm generating. This is why it's calling the issues. I was suspecting that, but I want to. If you try only like 10, okay, let's do 10. Let's do a more robust. Thanks, Thor. Where are you here? 10. Yeah, there you go. I have 10 chains objects that I generated from a prior predictive distribution. This is what I'm doing. And the nice thing about summary stats, I think it's a method from data frame that I might be wrong, that the guys in Turing, they overloaded it with a method for our chains object. So if you run summary stats in a chain object, that's everything that's returned for a sample in a Turing model, you have this nice summary statistics. That's a whole data frame. And you have the mean, standard deviation, naive standard error, Monte Carlo standard error, effective sample size, R-hat, that's horrible. And we also have effective sample size per second. And this is something for you to see how fast your model is generating samples. Because I'm using here, I was using Metropolis Hasting. It's fast, but it's not so good because it's random walk Metropolis. We can do better with nuts, for example. And also we have the quantile function. We pass that same chains object to the quantile function. And by default, we have the median, the 25 and 75% quantiles, what we call the Q1 and Q3 in classical stats. And we also have the 2.5 and the 97.5% that encompass the 95% quantile range for the values of this parameter P here. So this is how we inspect the chains. We can also If you have a big model, we don't want to have all the parameters. We just want a couple of them, or just a subset. We can do group and our chain object and then pass the parameter. Or we can also do an index. Group, it doesn't accept a list of parameters. It just accepts a symbol. You cannot pass a list of symbols. This is something that I wish Turing would do. Is something for everybody who wants to get involved in Turing. Maybe do a nice contribution here. And also we can do an index here, treat it as a multidimensional array. I want all draws from columns 1 to 6. So that's from the first to the 6th parameter. And then I want all the chains, because if I run multi-thread, we have a third dimension here. That's the number of chains that you ran. So we can also subset our chains object with these, and then we can pass these to a summarystats or a quantile function, and we will get only a subset, only summary statistics or quantiles for that specific subset of chains. Yeah, that's what I did here. So I only have one parameter, so this is like one column. And then I get all draws, all chains for that one single parameter. I can do that. If I had like 100 parameters, I can kind of do like, okay, I just want the first 10. That will work. This is a nice way for you to subset a chain and not have to manipulate, convert the summary statistics to a data frame and then filter and everything. So you can just do like an indexing and a slicing in a chain object. Yeah, you can do that also. Yes, you are right. You can do something like this. Force Brew just told us in the chat, you can do something like this. Actually, here is chain. That will also work, and then this will return all the draws, and then you can do summary stats on that object. Yes, thank you so much. I will insert this afterwards and update the whole notebook and the whole workshop. Thank you. So plotting chains, we have a lot of options. The default one is the plot. That it's a recite for the plots.jl for a chain object, and it will do a trace plot side by side with a mixed density. So this is a trace plot on the left, because we have small samples. Let me increase that sample size for us to have more samples. Where are you? Here. Let me use like 2,000 samples. And now we have a trace plot here for our 2 samples. And we have our parameter density. And if you have more parameters, it will stack those trace plots side by side with the mixed density for more parameters. So it's a nice plot, and also you can subset here your chain if you want to, with all those methods and slicing for your chain. If you put like color dimension equal chains, every chain will have a color, or you can have color dimension a parameter. Since here I have just one parameter but 2 chains, it stacked horizontally 2 chains with only 1 parameter. But if I had more parameters, they would be like a mixed density for them here, and it's a good model for you to use it, visualization. But I suggest for you to subset your parameters, because some parameters are like in 0 to 1 scale, others are in another scale. So be aware of this. this is the plot default. The default recite when you plot a chain object from MCMC. Now we have several plots to choose from. So these are classical Markov chain visualization plots. We have a trace plot. We see the chains. Oh, let me correct this convergence. We use a trace plot to see if the chains converged. We have a mean plot, that's the running average of your mean per interaction, and it should be stable. And it should be a signal that your Markov chains has converged and they are stable to be sampled. We have our density plots that everybody knows. It's the full density of our full posterior density of our parameters that our model perform inference. We have mixed density, histograms. If you want parameters that are that if you want a more like discrete visualization of your parameters, you can use a histogram with the bars. And we have also autocorrelation plots. And I kind of plot everybody here for you guys to see. So this is the trace plot for only one parameter. If I have more parameters, the plot would accommodate for more parameters. I have the mean plot. I have the density plot is this one, the histogram for both chains, the mixed density for also both chains, and I have the autocorrelation plot. This is the lag, and also for both chains. And also there is an option that if you want to construct your plot, you can do this. You can have a special keyword argument in the plot recite for the MCMC chains object. You can say, okay, I want the mean plot on the left and the auto plot on the right. So this is something quite unique. And you constructed your whole custom plot here. And then you can save the plots by using the default save methods from the plots.jl. And also there is one special plot. It's called the corner plot. And I hijacked a model from below because I haven't run yet multi-parameter models. So this is another model from below. It's the SRI model that have the Y and the beta. And with the corner plot, you just do corner your chain, and I use a keyword DPI that's to have the better visualization for the plot. And here it's you have kind of a pair plot of your MCMC estimates side by side using two parameters at once. So this is gamma with beta, and this is phi inverse or reciprocal phi with beta, and this is the same for reciprocal phi with gamma. So now let's go to one thing that was already asked earlier. How do we avoid for loops inside the model macro? We have two things. We have lazy arrays and filldist. So for example, let's take a logistic regression model. How would you code this model using a naive approach? So you say, okay, I have a matrix of data X. I have a dependent variable or a response variable Y that I want to model, and Y only takes values either 0 or 1. So it's a binary discrete variable. And you can also do something like this if you want to make to have the model a better signature and also type stable. But Turing does a lot of things that automatically is more type stable, and you don't have to specify what your arguments types are. And then I have semicolon, then I begin with my keyword arguments. And then I say, okay, I have the number of predictors, the size of the columns of my X matrix. And then I begin the model. I specify my priors here. I say, okay, alpha, a normal, mean 0, 2.5 standard deviation. And then I instantiate a vector of floats, undefined, with the size of our predictors. So with the size of the columns in the X matrix. And then I do the naive for loop. Okay, for every observation in one toward predictors. Okay, you do like beta I. It's a normal, and I don't specify anything. So it's a normal 0, 1, standard normal, mean 0, standard deviation 1. And then I end the loop. I go to the likelihood, and I say, okay, for all observations, please sample or my likelihood is a Bernoulli logit with the alpha, the intercept, plus the columns, the observation, the vector of observations times, this is a dot product. This is the C dot, or you can use like dot, the function, times my vector beta. So this is a dot product between the x's for that specific observation and my model, my vector of coefficients betas. And then I end, and also just a note, Turing Bernoulli logit is the safe logistic parameterized Bernoulli distribution that already converts the log odds to probability. So it will do the whole link function for you in the logistic regression model. And it's a safe logistic. So you won't have any problems with having numerical issues. So you should use it. Now, how we would remove the for loops. I don't think who said that. Let me see. I think it was, yes, Matthias. So you can do something like this. So like he said, we can use the dot to vectorize, but it's more efficient for us to use the array dist and the lazy array. You will have more performance because somehow I cannot explain. It's more performant if you use a lazy array, and if you also use the array array of distribution. That's this function in Turing with the lazy array. It's a lazy evaluation of this distribution, and you enclose everything in an array dist method or function. This is similar to something like this. This is similar to something like this, but this is better using the array dist and the lazy arrays. So when you do the array dist, you have, oops, cancel. You have a new distribution that's kind of an array of distributions. So this is how Turing deals with for loops. And when you use the lazy array, you lazily wrap an object, and you wrap the whole computation using an array to another array, and that's the macro. It creates a lazily broadcast of the Bernoulli logit for all the alphas, and I vectorize a sum here because I'm now using like arrays. So I have to vectorize a sum, otherwise I get dimension inconsistency. And then I do a whole matrix multiplication, X, our matrix, times our betas which is our beta, our coefficient vector, and the size of our predictor. So this is how you would get rid of a for loop. Now I have an example to show how fast and better that whole approach is. So I don't know if everybody is familiar. We have a very well-known data set. It's called Wells from Gelman. The first book before the BDA book, the Bayesian Data Analysis, you had a book that he coded all using bugs, I think. It was 2007. And most of those examples, they are now translated to Stan and Turing, and you can go ahead and use it. So we have a data from a contaminated region in Bangladesh that we have around 3,200 residents, and there is arsenic contamination. Arsenic is something not so good to have in your water supply. It's highly toxic, and then they assessed responded if they change it, they switch it wells regarding to some parameters. So our dependent variable is switch, either if the respondent switch it or not. His well, his water supply. We have arsenic, that's arsenic level. I don't know how measured, how to interpret those units. We have distance, that's in meters, from the respondent's house to the nearest well with safe drinking water. We have a binary variable, that's association, that it's 1 if any of the members of the household of the respondent participate in community or organization. It's a member of the community association. And we have education, and it's the number of years that the head of the household of the respondent have. So those 4 variables would somehow influence if a respondent would switch or not to a safe drinking water. And then here's something just to get the data. I make like XWell, it's a matrix without the switch variable. So it's all the data without the dependent variable, our Y variable, the switch, and Y wells is just all observations of the column switch. So it's just an int64 vector with 0 and 1, and here it is. Our whole 3,200 observations. And why we would get rid of the for loops, because I have here benchmarking, and I'm passing the reference to not let Julia optimize the whole compiled benchmarking run. So if you take a look, just using like 100 samples, we can use more samples, but I don't want to break this notebook because I have more stuff to cover. If you take a look, it's more faster. It's faster if you run the logistic regression vectorized. It's the same data, the same sampler, the same number of samples, of posterior samples. The only thing that I'm modifying is here I'm vectorizing things with arraydist and lazyarrays, and here I'm doing the naive approach with logrev. Both with a for loop. Both approaches are pretty fast, but the vectorized approach is faster. So always try to do that. And also the second thing that you will do that is that some autodiff backends, they only work if you don't have any for loop inside your model macro. So Tracker and Zygote, it's the 2 Flux.jl autodiff backends that Turing can use. They don't work if you have a for loop. So you have to get rid of those. Then you use like arraydist and lazyarrays. And a quick interlude to which autodiff backend to use. This is something interesting, and you can also specify in Turing. So we mainly have two types of autodiff, and this is a link to a Wikipedia article. If you don't have any idea what automatic differentiation is, don't worry, go to this link and find out. And if you also have more questions, I had a rough time getting my head around this whole idea of automatic differentiation. So this is a nice YouTube video that explains what's forward mode, reverse mode, and everything. Both modes use the chain rule to go from an input in n-dimensional to an input to m-dimensional, and the forward autodiff, it's better when your inputs are larger than your outputs in dimensionality, and reverse autodiff is better when your outputs have higher dimensionality than your inputs. Mainly in a neural network kind of things, the reverse autodiff are better. And yeah, Seth and Thor, nice to meet you guys. I always interact with you guys in forums and Slack. So they are correct, yes. And you can use for loops with Zygote, but it will take a huge performance hit. It's better to get rid of for loops at all. So always try to get rid of for loops. Thank you. It's easy to set your AD backend. You just use Turing, set AD backend, and then you pass symbol for your backend. Yeah, sorry, I spoke the opposite. Yes, if you have more outputs than inputs, oh, this is wrong. No, yes, if you have more, oh, it's wrong. Yes, yes, you are right. Let me correct this. No, I think it's right. This is when autodiff forward mode, it's better. And the reverse autodiff is when you have more inputs and less outputs. This is why, thank you. This is why neural networks use a reverse mode autodiff, because they have a lot of inputs and just one output, like a cost function. And for diff is Turing's default, because most Bayesian inference we have like one output or few outputs and a lot of one input, few inputs, and a lot of outputs. So this is why Turing's default is the forward diff, the forward mode autodiff. And how do you set your backend? You just use a Turing function called set AD backend, and you choose Zygote or tracker. And also a caveat, you have to import your backend in your Julia session. So next to Turing, just do like using Zygote or using tracker or using reverse diff or whatever backend you will use. There is a new backend coming soon. I forgot the name, it's something Yoda something. And there is a lot of hype, and people are saying that it will make everything a lot much faster. So more things are coming in the AD backend in the future. So now let's talk something about how to make hierarchical models. So this is the whole text explaining what are hierarchical models, but the main idea is that we have something called hyperprior, and this is this parameter here called phi. This is our hyperprior, and all of our other parameters, theta, they are sampled for that. They have a prior that depends on the prior of phi. So phi is a hyperprior for our hierarchical model. And the whole idea is that when you have different groups, or you want to model heterogeneity in your model, in your phenomenon, you use those multi-level models or hierarchical models or mixed models. They have, or random effects model. They have many names, but they are almost the same. It's that one observation from one group of parameters, it will inform our hyperparameter, and we can use that uncertainty and propagate to the other inferences that we will use for our group level parameters. So we can have a better inference if our model is nested. We have several different levels of observation units. So this is something nice that we can take advantage of that nested structure of our data, and we can use that to have better inference for our group level parameters, and we also can have a more coherent modeling of heterogeneity. That's the whole deal with hierarchical models. And this is the figure of the hyperprior. And basically, we have three approaches to multi-level models. We have the random intercept model, where we give each group a random intercept, a random base rate, as you might say, in addition to the whole model having a global parameter, a global intercept. The second approach is that we give a random slope. So each group receives a random slope for each, or you can choose a subset of the independent variables, in addition to a global intercept. And then also, I forgot both a different intercept. There you go. And then we have the mix of those two. The third approach is that we have the random intercept slope model. So we use both approaches, and every group has also a random intercept, a group level intercept, and slopes, in addition to a population, sorry, a group level intercept and slopes, in addition to a population level global intercept and slopes. And this is the whole mathematical notation for the model. So our likelihood, okay, let's start from the bottom. Our model has some error. We use like a long tail distribution to concentrate our errors towards zero, but also giving space for having like wide errors. But we want those errors to be concentrated around zero. So we give something like a exponential or a log normal or a truncated Cauchy with only being positive. Exponential is interesting because it only has domain in the positive real numbers. So it will always be positive. So we will specify something here, a lambda parameter for the sigma. And then this is the hyperprior. We say that our parameter tau here, it's a Cauchy, which is a fancy name for a student's T distribution with one degree of freedom, only positive. So it's a truncated Cauchy with mean zero and a standard deviation something that we specify. And then we say that we have a global intercept. This is the alpha here, which takes a mean something and a standard deviation something. And then we have, here are our group level parameters. And every group has your own local group level intercept, which is a normal with mean zero. And here's the hyperprior. This is the parameter tau here that itself is a probability parameter, is a parameter to be inferred. And this is what generates the whole uncertainty in propagation and how one model or one group informs the other groups, and we have better stable inference and a better propagation of uncertainty. This is the whole trick or the whole soul of hierarchical models. And then our betas, this is a vector. We say that they all have distribution normal with some mean and variance. And how we will do something in Turing, I generally use this approach. I say, okay, model vary intercept. I have a matrix X. I have a vector of group IDs. That's the same length of my observations. I have a Y as before, and now I have some keyword arguments. So I have the number of group, it's the length of the unique entries in my group ID vectors. And then I have the predictors, is the same as before, is the size of my columns, is the number of columns in my X model matrix, my X data matrix, and then I begin specify the priors. Generally, I use like a normal with the mean centered in the mean, or you can use the median if you want to do a more robust prior of my dependent variable, and then I get 2.5 times the standard deviation of this dependent variable. And then I use the filldist to fill all the predictors. It's nice also for you to center your predictors and standardize them with mean 0 and standard deviation of 1. It will be computationally better for you. And for the MCMC sampler also, it will ease its job to sample, to traverse the whole posterior geometry if you standardize your X matrix. And then we set sigma as is exponential, and stand defaults if you want if you run like rstan arm, or if you go to the whole literature, we use an explanation with the fraction of 1 divided by the standard deviation of y. This is like the stands default in rstan arm if you run this. And here is the random, the multi-level stuff. So we have a parameter tau, and we use a truncated, and this is something nice because you always use the truncated with the lowercase. This is not efficient. If you use with lowercase, Turing has some nice custom distributions for when you truncate distributions with a lower bound and an upper bound, and you have to specify them with lowercase truncated. So this is a performance gain. Always use truncated with lowercase. And here's a Cauchy. I put like the psi standard deviation of my Cauchy. I put like something like 2, and I truncated it for a lower bound of 0 and an upper bound of infinity. So it's defined in the whole positive number line. And then I begin with my alpha J's. And this is something nice because I can use Unicode stuff to specify models in Julia and Turing. This is something really interesting. And this is a filldist, so it's a vector it's a vector of distributions. All of them are normal with mean 0 and standard deviation tau. That's the hyperprior. And the size is the number of the groups. So these are all the group level intercepts. And then I do a likelihood. I kind of broke down for easiness for you guys to see better. I have a linear predictor that's y hat, that's alpha, and a vectorized plus x times beta, because I have my global coefficients times my model matrix, and then I add alpha indexed by my model local coefficients, and then everything is a multivariate normal. It's an efficient normal vectorized, and I say that mean, my linear predictor, and standard deviation sigma. And this is how I do a random intercept model. The random slope is similar, but instead of having alpha j's, I have beta j's, and it's the same. So, but now I have a matrix of coefficients. So the matrix has lines the same number of rows as predictors, and the number of columns as the number of groups. And I do the same. I only changed this guy here. And this is how I specify a random slope. And the mix of those two, it's the random slope intercept model. And I'm missing here something. So this is what I should do, random slope intercept slope model. So this is how I will do the random, oh boy, it's random intercept slope model. So this is how I would code the random intercept slope model. This is like the mix of those earlier two approaches. I have the alpha j's and the beta j's, so I have to specify two hyper priors, tau alpha, tau beta, and then I do like a mix of those here, and then I have to do the linear predictor has more entries, but it's the same logic. This is how I would specify a random intercept slope model in Turing. So any questions so far? This is like Bayesian modeling 101, like hierarchical models, how to inspect chains. Now we will go to the crazy stuff, things that Turing does, and I find it very interesting. There is a lot of things. I will cover just two that I find really nice. I will cover like discrete parameters, hidden Markov models, and models with ODE. I think that the real advantage of Turing and the whole Julia ecosystem is that if I want to have an ODE system in my model, if my model has to solve some sort of differential equation systems, I don't have to code it up in Turing. I just use different equations. I just have to use a solver from different equations and plug it in Turing, and it works right out of the bat. So this is nice. For sprue, I will say this in the hidden Markov model. I don't know if it's the right approach, but that's what I've tried to code, and it took me some hours of research, and this is the best thing that I find out. Maybe the guys at the audience have some better ideas, who knows. So this is we have a hidden Markov model, and this is a model that we have discrete states that are latent. We don't see them. So this is used somehow like in animal tracking models, in ecology models. You have something like this because you have some discrete states that your observations have, and you don't see those discrete states. Or a nice example is if you are monitoring sleep, we have roughly two states of sleep: the REM sleep and the non-REM sleep. So we have different activities if somebody is in one of those states or another. So to give an example, here is a simple model, and we have two states. I colored them in orange and blue. So one state has like min 10. So every time that this model is in this state, it will generate a Gaussian variable with mean 10 and some standard deviation. And if we play around with those sliders, you can see how those states generate like data. In the real world, we don't know the states. They are hidden from us. That's why they are latent. And we have to estimate them. How do we do that? Instead, we use something standard does not tolerate discrete parameters, because everything has to have a derivative. Everything has to add to the gradient and to guide the Metropolis Hastings proposals in the HMC algorithm and sampler. And I love STEM. I use it on a daily basis almost. And NUTS and HMC samplers, they cannot tolerate discrete parameters. So this is a problem. Solution, we marginalize them with the law of total probability. We don't know what the probability of a state, so we marginalize. We sum or integrate. This is a discrete parameter, so we sum all the probability of the states, and then we have the whole probability and we marginalize. I will show how we would code this in STEM using marginalization, and then let's see how you will do different in Turing. There are several ways for you guys to deal with a Markov, hidden Markov model if you want to marginalize out your parameters. There is the filtering. It's also called forward algorithm. There's the smoothing, also called forward-backward algorithm. And there is the maximum a posteriori estimation, that the map, also called the Viterbi algorithm. I will cover the forward because it's easier and we don't have time to cover all of them. And also because I haven't studied the others. So I'm not an expert in hidden Markov models, but this is a very good reference. You go ahead and if you want to dive deeper in what are hidden Markov models, go to this reference. So what are the hidden Markov models? This is the whole maths. So we define the fourth variables as a vector of alphas, and they begin at a time t. And for every time we have a delta t multiplying a matrix gamma of our yi variables, and it's some sort of a Markov system, because for every distribution in time, the only thing that depends on that distribution is the previous states of the system in t-1. So we have an unobserved transition matrix that we don't know. We need to estimate that it's gamma, and this matrix we kind of have them for it's a symmetric, not symmetric, square matrix, and we take its values. So if you want to know, how do you say exponentiate? We do exponentiation with the time t, and this is our matrix. And we have also the state distribution unobserved, that we don't know how the states are distributed, how the transition of states are distributed. And we always give like a prior, like a Dirichlet with something vector. Here is a vector nu or any other parameter name. And we always use a prior like this. And then we can have the marginal likelihood by summing over all the alpha t for our matrix J, for all our entries of our matrix J. And in in matrix notation, it's a vector multiplied by a row vector of 1. So you sum them up. It's kind of a dot product of a vector of alphas with a row vector of 1s. And also one of the assumptions, there are several, but one of the major assumptions is that the matrix gamma is full rank, so no linear dependence, no zero eigenvalues, that kind of things, and ergodic, so it will converge asymptotically to a unique stationary distribution in the limit as t goes to infinity. So these are the basic assumptions. And this is the example for Lewis Barajas, and they have the whole stand model there. It's a true state hidden Markov model. It's actually this guy here with mean 1 and with mean mu1 as 1 and mu2 as 5. So it's this model here, this random generated data. And we need to know what are the means of the states. So in stan, we would code something like this. Where is the stan? Oh, it's here. So we would say like, okay, here's our data block. We have k states. We have some number of times, and we have an array of reals, of floats. That's y that has the same length as the number of times. And then we have, this is the Force-Bruce question, because we have a positive ordered mu, that's the state-dependent parameters being the same. Yeah, that's it. Tor nailed it, because I was trying to, I fussed around with the bijectors, but it's too highly advanced for me now, and I had little time to dig all the documentation and source code from the bijectors. But you should use something in the bijectors. I don't know if it's implemented yet or not, but if it is implemented or will be implemented, it will remain, it will be found in the bijectors.jl package in the Turing ecosystem. This is where all these whole positive constraints of your variables, of your distributions will be in the Turing ecosystems. And then we have a simplex data. This is what we do. This is the transition probability matrix. And then we code our priors. We use a Dirichlet. We use somehow a robust fat tail distribution, a student T with three degrees of freedom, mean 0, standard deviation variance 1. And then we have here is the forward algorithm. We have a log prop and a accumulator, a helper, a vector. And then we do a forward pass. We do for the first observation. We accumulate the log prop of YY of our first observation, given our mean of our first state, and we do this for the both states, and then we loop all over the other observations for all the other states, and we do this kind of people in machine learning know this as the log sum X trick. So, oh, nice. So Tor just told us it's not yet implemented, but if people want it, the people is going to get it. Yes, I desperately need it. And I couldn't also get to work the simplexed bijector with the Dirichlet. I had a lot of problems. So maybe I'll need some details on how to do a simplex using a Dirichlet in Turing. But that's it. Tor, who's one of the guys involved in a lot in Turing, in the development, he will implement those things. And if anybody wants to contribute and help, you are mostly welcome to do so. And so we loop for all the other states, and then we use this helper variable accumulator, and then this is where we accumulate the marginal probability of our hidden states, hidden discrete states. So we do this log sum x, and for numerical issues, this is a efficient and safe way from numerical underflow to do a log ask and sum all the exponentials and then take the log. So log sum x will do this. This is a shorthand for this, but in a safer way, efficient and without running with numerical underflow issues. So, and then you do the target plus. You can do that also in Turing. You can use the Turing macro add log p, and it's the same as target plus equal instead. And then you add to the target log probability, you add the whole marginalized states over the probability for all the states. So this is how you will do it instead. In Turing, what is nice is because you can do a whole composition of samplers. This is really crazy. I like this a lot. So here is what we will do in Turing. I will go to the model later. Let me just show you what's going on here. So I'm specifying a composite sampler. This is really nice. I'm using like nuts for all my continuous parameters. That's the mu and the thetas. And I'm using particle gibbs because it's a discrete parameter for my s's, for my states. So my vector of states will be a discrete vector of either 1 or 2, and I'm telling Turing, okay, Turing, these parameters you are going to use nuts, which is a Hamiltonian Monte Carlo algorithm that's only take continuous parameters, and for the discrete stuff, please use particle gibbs that tolerates also discrete parameters. And this is our composite sampler, and this is the model without the marginalization. There is one caveat. I need to instantiate a T-array from libtask, a T-array object that will hold all my S sampling variables that will be sampled using particle gibbs, because particle gibbs, they need to have a T-array object to store the samples. And this is the only caveat here. And oh, how I did the positive ordered, this is okay. Who asked this? It was Force Brew. So Force Brew, this is kind of a hack. It's not efficient, but this is how I did. I just put an if statement. If any of the mu i's is higher than the mu I plus 1 for all of my mu's, if this happens, then it's not positive ordered, and I tell Turing to reject the sample. I just add to the log prob minus infinity. So Turing will reject the sampling, and we'll try to do another sampling. And this is a very nasty hack. It's not efficient, but this is something that you can do it. The better way would be to have a bijector, as Thor said. But this is what I found to do the hack, to have a positive ordered, and to have the simplex in the thetas. There is something in the Turing's documentation in the bijectors, but I could not get it to work, so I gave up. And I spent a lot of hours, so it's not something trivial. And then we run this thing, and then we pass our composite sampler. I just ran like 20 observations, 20 samples, because 20 posterior samples, because this is kind of heavily computational. So I don't want the notebook to take like half an hour to load, you know. And this is what we found. It's way, way, way far from our ground truth, but if you sample enough, it will converge. So this is something I find it interesting, but in real life, I wouldn't do a hidden Markov model using a Gibbs. I will do the whole stand approach in Turing and do the marginalization because it is much faster, it is much robust, and it will also recover all your parameters. So, but this is like a nice example of the composite sampler that you can use with Turing, and you specify this using a Gibbs. And Gibbs is not a Gibbs sampler. Gibbs is something that I don't know. It's not intuitive, but Gibbs is a shorthand for you to specify a compositive sampler, and then you pass in like what samples do you want, and then you pass the symbols of the parameters that you want that sampler to sample, and it will use a compositive sampler. And now let's do ODEs. This is really nice. I think that this is the main advantage of Turing because it uses the whole ecosystem of the ODE solvers in Julia, and they are pretty fast. If you go to Stan, you have to wait for either guys at Stan do like a whole interface of the CV ODEs from Sundials, the Sundials C++ library that uses the ODE solver. So Stan mainly uses Sundials as an ODE solver, and they have to implement a very complex interface for you to plug ODE solvers in Stan. And Turing is interesting because you kind of decouple the development. So if people in Turing don't want to work in interface for ODE solvers, and there's a new ODE that's compliant with the differential equations.jl, I guarantee that it will probably work right out of the bat in Turing. So what guys are doing, what the developers are doing in differential equations.jl, you can use it everything in Turing, and you don't have to create like crazy bridges or crazy interfaces. And this is where I think the Julia whole ecosystem really shines. And this is I will use an example. I think that one of the authors of the example is in the audience. I think it's Liz Semenova. I don't know if she left, but she was here before, and it's a nice example. So this is kind of in fashion now because of the whole COVID thing. We have ODEs in Turing, so susceptible, infected, recovered model. It's basic compartmental model that people, they move through those compartments. They begin in susceptible, and then you have a beta. It's a kind of an infection rate. And this moves people to the Y, the infected. And you have a kind of a recovery rate, gamma. And in some models, you also have, unfortunately, you have the death rate. And people that are not recovered, they unfortunately migrate to the dead compartment. And this is the susceptible. This is the susceptible, infected, recovered models. And it's governed by, the whole dynamics of the model is governed by a system of differential equations that we have the susceptible, it varies by the fractions of infected by the whole population, and the beta, the contamination rate, and the constant rate of infection contacts, negative, multiplied by the number of susceptibles. And then we have the infected, they vary the positive of those minus the people that will be recovered. And the recovered, they vary, the derivative with respect to time is the recovery rate times the number of infected in time t. So this is the whole differential equation modeling here that we have. And how do we code this in Julia? Simple. We just use differential equations.jl. and then you kind of download the package using differential equations.jl. You code an ODE function, and this is a function with a bang, so it will have side effects. It will change its arguments, so it will change the derivatives specifically here. And so I have a du, that's kind of the standard nomenclature, standard notation, du, u, a vector p of parameters, and a time span t. So I say, okay, I unpack the vectors in tuples, and then I calculate our whole population by summing up the three possible compartments. And then I say, okay, infection is the beta times the infected divided by my population times the susceptibles. The recovery rate is the gamma times the infected. And then I do a begin here. And this macro inbounds signals Julia to say, oh, forget about array or array index checks. Go ahead, go nuts. Don't check for indices because I know what I'm doing. And you will not index something wrong here. So go ahead and you disable this and use it with caution. But if your model runs, if your ODE function runs, you can, and it's bug free. You can turn on inbounds, and you have like a huge gain of performance, and it's always nice to have it. And then our derivative, it will change this argument. So this du, that's why you code it with a bang, to have the notation in Julia that function that ends with a bang. Caution, they have side effects. They will alter, they will change their inputs. It's not a pure function in a functional programming jargon. So the first derivative, that's the du1, it's minus infection. The u2, it's the infection minus recovery, and the u3, it's recovery. Since it's a function that will have side effects, we return nothing, and then we end the function. And this is what some simulated data show. So if you have our y, this is the number of infecteds in time 0, and if we play around with those sliders, we can see that the curve, this is the number of days. This is the curve of the susceptible by the number of the days. And if you change the number of infected in day 0, of course, the number of susceptibles will go down much faster. And these are the real things that we are interested in. What is beta and gamma? What is the mean infection rate, and what is the recovery rate? So how long does it take for people to recover, and how long, and what is our beta? So this is the main things that we are interested. And if we know those things, we know how the pandemic or how the infection will behave in the future. So this is what we are interested in. And if we change those things, it will change the whole system, and it will change how the susceptible, the infected, and the recovered will progress over time. So we are interested in those parameters. And how we do that? So this is the boarding school example from Griestein et al. 2021. And it's an outbreak of influenza virus in 78 at the British boarding school. The data consists of some daily students some students that stayed in bed in a 2-week period. So, and this is how the infection progressed. This is the number of students that were in bed. So these are our cases. And this is how we would do an ODE in Turing. So we would provide the cases and the number of infected in day 0. And then we have a vector of betas. Oh, sorry, vector no. Ooh. A truncated normal. This I'm using Turing's efficient truncated normal. So This is a better version of the truncated normal with mean 2, standard variance of 1, and I truncated to being a little bit positive and 10. And I'm using 10 instead of infinity because I had numerical issues. The same with the gamma, it's a truncated normal, positive, constrained to a little bit positive and 10, and which means 0.5, variance of 0.5, and 5, it's the over dispersion rate in the negative binomial likelihood, and a dispersion parameter. So we called the reciprocal phi that I kind of gave the notation as phi inverse, and we say that's an exponential, and I give kind of some boundaries to not avoid numerical errors, and I calculate phi as the inverse of the phi inverse. And this is the ODE stuff. So our U, it's all our compartments, but as a float, because that's how the whole interface of the differential equations.jl. I also construct a vector of parameters as beta and gamma. I construct a tuple of time spans with beginning of 0 in floats, and also the float of L, and L it's the length of case, so it's the length of time that we have our observations. And then I instantiate ODE problem. I say, okay, ODE problem, this is the constructor. I pass in a ODE system. I pass in the U, that's my compartments. I pass in a time span and parameters, the vector of parameters, and then I call solve my problem, and we are using Tessitura's 5th, 4th order. It's an efficient Runge-Kutta. The Germans will get very upset. Runge-Kutta algorithm, and it's the dormant prince. But the Tessitura's, it's 10% faster than the dormant prince, and Stan uses the dormant prince because we don't have Tessitura's yet in the sundials, then we cannot implement in Stan. And then this is the solution, and I get only the infected from the solution, and then I plug it in here in cases, negative binomial, only the infected for length of time with my dispersion parameter from the negative binomial, and this is what I get back. So this, I did the whole thing. I did like nuts, 1,000 warm-up samples using a target accepting rate of 0.65, and using multi-threaded 2,000 parameters, and also 2 chains, but we can do more. We can do like 4 chains to use like the Stan defaults. And then we have a summary stats, and these are summaries, and it pretty much got everything right. So in our example, in the influenza 78 boarding school in UK example, our beta, they are somewhat 1.9, and our gamma is somewhat 0.9, and this is the whole trace plot. So the chains converged, and also this is the whole density for both chains in our beta and gammas. So we have a nice density of that captures all our uncertainties of our parameters. So this is what really gets me excited in Turing, because it's how the interface with the whole Julia ecosystem, specifically the differential equation solvers. How are we in time to have more like 20 minutes? Can we go?
We already exceeded 20 minutes, so it's quite interesting. Therefore, I was not interrupting, but yeah, I think we should come to an end soon.
Okay, so just for you guys to revisit the notebook, we have something called the funnel of death. it's a new funnel, and what's the problem here? We have a variable that's that nuts or HMC cannot sample efficiently, because if you take a look at the funnel, the neck, the top of the funnel, you need different values of epsilon and L. You need a small epsilon and a high L to traverse all this parameter, all this space. And in the bottom of the funnel, you need the opposite. You need low epsilon and high L to take like small steps and a lot of steps to escape this funnel. So, and nuts cannot do that because HMC cannot do that because you have to set epsilon and L fixed. And nuts, you can automatically set epsilon and L during warm-up. It can vary, but during sampling, it's fixed. So you are stuck in the funnel of death. How do you do that? You do a reparameterization, and the funnel becomes something like this. It becomes something quite easy because you don't need to fuzz around with the whole optimal epsilon and L. You can sample, you can explore the whole geometry of the posterior, and this is how you do non-standard parameterization. And you guys take a look afterwards, and you can recover back your parameters by using like something like called map slices, which are basically a function that maps a function to each slice column of an array. And also there is the QR decomposition that can speed things up because you decorrelate your predictors, and you also alter the geometry of the posterior to make it easier for the MCMC sampler to explore. So this is the whole math. We can do a QR decomposition in a matrix X, and then we can recover back our betas by using the inverse of the R in the QR decomposition times our beta that we use it that we estimated from Turing. And here's an example, and take a look at the effective sample size per second. So if you take a look, you have more effective sample size per second. And also, when we transform the parameters back, we have a huge gain in effective sample size. So we have like 2K, 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 and 1200 in our betas. If you go see the normal without the QR decomposition, we have 1K, 1K, 2K, and 1200. So some parameters that were correlated, we have better effective sample size if we do the QR reparameterization and then recover back, construct back our betas from the QR decomposition. And that's it that I had for you guys. These are the reference, and thanks for the opportunity to show you the Turing, and thanks for Stuttgart, Julia Groups, and also for Julianne for the opportunity.
Thank you very much for this nice presentation. I think we can invest another 5 minutes if there are open questions. Okay, I think you answered everything.
Yeah.
Okay, then thank you again